So it's a great pleasure to hear from Jesper, Jesper Jacobsen, and he'll talk about a model that we all know and love, the three-state plots model. Thanks, Jesper.
Thank you very much. So it's some kind of pleasure to be here, but I'm very sad that Rodney passed. Rodney has meant a lot to all of us. It's one of the persons who has contributed the most to statistical physics since ever the field was initiated. And in this world, which is rapidly evolving and not always for the better, it's reassuring to know that the contributions of Rodney will stand forever and serve as some inspiration for us and for future colleagues. I regularly read the preface to his famous book because I think that some of the lines so clearly ring true, namely that if some model is worthy of interest, it should be studied by all available means, and I think that's a very good lesson. I think I first met Rodney rather late in 2010 at StatPhys in Cairns. I narrowly got a very good picture of him. He was sitting next to Yang. The problem was that somebody pointed out that Yang should have sat to the left and Baxter to the right. While we were hoping that they would change places, I fetched my camera, and of course they refused to comply. So somebody got the good shot of Baxter and Yang, and nobody got the picture of Yang and Baxter. So today I'm going to talk about an algebraic approach to interfaces in the three-state plots model. It's work done in collaboration with Augustin Lafay, currently in Helsinki in Finland at Aalto University, and Azad Gainuddinov, who is in Tours in France. And more lately, we have also started collaborating with Johan Lee, a joint thesis student on this subject. So loop models presumably need no introduction in this audience. So it's self-avoiding simple curves in 2 dimensions that can be modeled on a lattice or directly in the continuum limit. And a famous model studied in particular by Bernard Nienhaus on this in this realm of models is depicted here. So you take a hexagonal lattice and then you draw loops on it. And the basic idea is to give loops a fugacity n. And there are also some local weights, x per bond. And if n, the non-local weight, is less than 2, then there are 2 critical points, a dense one and a dilute one. And the continuum limit of this model is very interesting. It can be studied by techniques of integrability, by techniques of probability theory, by field theory, and presumably other techniques as well. And it has been studied as such by many authors, some of which have been mentioned here, but many others are around. So the question that we got interested in some time ago was what would happen if we allowed for these loops, so to speak, to branch or bifurcate, so that they would form something more topologically more complicated than just loops. So if you do that, it seems that you should have some topological rules to give the weight to each component of whatever structure you would get. In analogy with the weight n that you give to loops here. So how could you define such a model? What would be its properties and what would be its possible critical behavior? Another motivation came from the fact that domain walls in certain spin systems having more than 2 components actually form such bifurcating structures. There are also other motivations coming from network models for topological phases. And the thing that we got interested in was some papers by Kuperberg on so-called spiders in invariance theory. So let me come back to that a little later. let me show a model that generates the structures that we are interested in. It's the three-state POTS model. So those two figures, they show two small neighborhoods, A and B, in a large configuration of a three-state POTS model shown as colors. And if you draw the domain walls between spins of different colors, you can see that the regions A and B, they get connected by some structure that is not just a single curve, but something that bifurcates. And this is the structure that I will be interested in here. So what you see here are actually two different kinds of correlation function in the three-state POTS model. One in which you have two domains of like colored spins, that's on the bottom, blue and blue, connecting A and B. And another one on the top where you have a domain, a red domain and a blue domain that connect A and B. So the domain walls between red and blue on the top picture can get very narrow because it can contract to just a single lattice edge. So that's a thin domain wall. Whereas on the bottom, where you have two different blue regions that connect A and B, of course, if they are to remain distinct, they cannot, the interface between them cannot be very narrow, so it's a thick domain wall. So it cannot contract to just a single lattice edge. And so one question that I'm motivated by is what are the critical exponents describing such excitations in a three-state POTS model? So to get there, we need to make some detours. So my motivation was already mentioned. What is a good model of webs on the lattice? So these bifurcating structures. And then there are all the usual questions about what are the fractal dimensions of this and that geometrically defined object. In mathematics, there is something around that is called UQSLN symmetry. So the usual loop model has a UQSL2 symmetry. And this algebra is commuting with the Temple-Elib algebra. So inside a small disk, the Temple-Elib algebra means contract two pieces of loops as shown on the left picture and do the same on the top part of the picture. If you change SL2 to SL3, Kuperberg had some construction that was called a spider, the A2 spider, which consists in doing the following thing. So inside a small disk, you indeed contract 2 points via some bottom arc. You do the same on the top, and then you connect the two of them by some vertical line. And that forms a pair of cubic vertices, and that's the algebraic generator of an algebra that, well, I will call the Kuperberg algebra. So let's see now how we can define a statistical model based on this algebraic ingredient. So as before, we take a hexagonal or a honeycomb lattice with nodes and links. And then we want to draw a configuration up top of it. And in that configuration, nodes can have valence 0, 2, or 3. In a loop model, they would have valence 0 or 2, but now they can have valence 3, meaning that there's some bifurcation. In addition, each bond, and that's something new, is going to be oriented in such a way that the orientations are conserved when you go through two valent nodes. Whereas when you have three valent nodes, you see 3 arrows going in or 3 going out. So a very simple sample configuration we'll look at as on the left part of this picture. So you see here 2 connected components, one of which is a loop, another one which is a bifurcating object. And in the bifurcating object, you have 2 vertices, one where 3 oriented lines go in and one where 3 oriented lines go out. In addition, I'm going to fix a fixed orientation on my lattice, which is called up. That's designated by the arrow. And I'm interested in the projection of the arrows of the embedded configuration on that fixed orientation so that each edge can be said to point either up or down. I need this direction for 2 reasons. First, I want to construct a transfer matrix for the model, so I need some time direction. And the second reason is that there's also some algebraic reason around. Indeed, what is propagating around loops in the usual loop models are fundamental representations of UQSL2. And here in UQSL3, I have two types of fundamental representations. The difference between them are exactly given by this arrow. So I have the fundamental representations with an up arrow, and I have the dual fundamental representation whenever a link is oriented in the down direction. So Kuberberg found that if you draw such a configuration, then you can reduce it to a number by applying three rules. So for a loop model, recall there would be just one rule saying that each loop should be replaced by the number n. Here, there are going to be three rules. So a loop is represented by a quantum number. Quantum numbers are defined on the bottom of the screen by the quantum number 3. If there's a small bubble inside a line, you take it out and replace it by the number 2, but you keep the line. And if there's a square, you replace it by a sum of two diagrams, a bit like in the Timberlake model. So the reason for having these three rules is the following. So if you think of the fact that at each vertex you need 3 ingoing or 3 outgoing arrows, it means that the cubic graph that you get, represented here schematically to the right of the picture, where you contract any stretch of parallel lines with valence 2 into one single edge in this abstract graph. This graph is going to be a cubic graph, and it's going to be a bipartite cubic graph because there's an alternation of vertices where 3 arrows go in and where 3 arrows go out. So that implies that the degrees of phases is always even. And one thing that you can relatively easily realize is that if you draw a closed bipartite cubic graph, then there is always going to be a phase of degree 0, 2, or 4. So less than 6, strictly. And so since these three rules tell you how to make a connected component smaller in terms of vertices, whenever it has a phase of degree 0, 2, or 4, it means that you can successively transform any cubic bipartite graph into a number by applying these rules. So that's relatively easy to show. What is more hard to show, and which Kuberberg showed, is that applying these rules in any order will lead to the same number. So that means that the statistical non-local weight of a bipartite cubic graph is going to be well defined by these rules. So we will call the resulting thing the weight of the configuration. And so now we are ready to define the model. So the partition function is the sum over all embedded cubic bipartite graphs. We are going to give some local weights to up bonds and down bonds. We are going to give weights to sink and source vertices, depending on whether they swallow or emit 3 arrows. And then we are going to multiply by this non-local weight, which is the interesting part of this model, which is called WK. So on the other hand, we could also think of the Potts model or any 3-state spin model, actually. So define a spin with 3 different values on a triangular lattice dual to the hexagonal lattice. Let's give each link of that lattice a weight x 0, 1, or 2, defined such as that the index is equal to the difference of the spins seen to the right and to the left of it with respect to this upgoing arrow. And let's normalize then by setting x0 equals to 1. That means that whenever we have a domain wall in this 3-state model, it's going to be given a weight x1 or x2, depending on its orientation. The partition function is going to be now 3 times the sum over exactly the same object as we had before, times x1 to the number of x1 type vertices and x2 to the n2 number of x2 type vertices. So this model, this 3-state model with local weights only, would be equivalent to the web model if the web model's non-local weight would be equal to 1 for any configuration. How could that be made to happen? Well, that can be made to happen if we play with the deformation parameter that we had in these rules before. We had this small q that defined the quantum numbers. So if I take q equals to e to the I pi over 4, and if I take, so there is the same number of sinks and sources, so y and z only appears in the combination y times z, so let's take that product to be 1 over square root 2. It turns out then that 3q deformed is 1 and 2q deformed is square root 2. If I absorb some part of the weight, 1 over 2 to the 1/4 into each vertex, the rules are going to be as depicted now. A loop will get weight 1. A tadpole will also get weight 1. And in the last rule, I get 1/2 of the first and 1/2 of the second diagram. So that means if you count the total weights on the left and the right-hand side, you always get 1. So those rules are probabilistic. So if I apply them to any configuration in the end, regardless of how I reduce it, I'm just going to get the number 1 and then I'm done. So that means that a 3-state Potts model can be represented as a web model if I take q to e to the I pi over 4. And if I take a special choice of the local weights, which turn out to exactly be related to the critical temperature of the Potts model on a triangular lattice. This can be generalized to UQSLN symmetry, but for lack of time, I will just flash some rules here. So the web model with UQSLN symmetry gives back the well-known loop model studied by Nienhaus for n equals to 2. It gives us the Kuperberg model for n equals to 3. And in both cases, there's a special point when q is e to the I pi over n plus 1, which in the loop model will give the dilute O of 1 model, alias the Ising model. And for n equals to 3, it's going to give the critical 3-state Potts model. So there are integrable spin models around with ZN symmetry. So it's sort of warranted to expect that we can find a special point that's critical for any n. But the web models, of course, has this deformation parameter. So the question is, can we deform these models away from this special point, and will they remain critical? And also, will they remain integrable? So to investigate the issue of integrability, what I'm going to show you today is that we will need some local reformulation of the model. So for example, for the loop model that was underlying the ON model, we would like to make it integrable by turning it into a vertex model. So there are 2 different ways that this can be done, depending on how the model is defined precisely. So as most of you will know, for the Q-state Potts model, there's a formulation of it in terms of a so-called Fortuyn-Castelline cluster model. And in that model, you can draw loops that run around the outside of the clusters and on their insides. And those loops are closely related to the Temperley-Lieb algebra. If now you orient those loops and do a special trick that was first figured out in a paper by Baxter, Kelland, and Wu in 1976, then you are going to recover a 6-vertex model. And so using this trick, you turn the Potts model in its FK formulation into a 6-vertex model, and then it can be solved by the techniques of integrability. If you take the ON model that has some dilution, you will need to do the same kind of trick, but you will transform it now into a 19-vertex model called the Isogin-Koropin model. And it was taking results for that model that Nienhuis was able to say so much about the ON model. So the locality enables us to define a transfer matrix or an R matrix, which is good both for numerical studies and to make contact with integrability. And it's also good for defining a Coulomb gas construction, which has played a big role in the study of these models, because the heights, they differ when you go through these vertices depending on their orientation. So the question is, can we take now a web model and can we turn it into some kind of local vertex model? And this is what I'm going to address now. So the basic idea in the loop model would have been to orient the loops and sum over two orientations. This is not what we are going to do here. Instead, what we're going to do is we are going to decorate the bonds by an extra degree of freedom that can take now three different values corresponding to three colors, red, blue, and green. So my configuration that I showed before will now be transformed into something like this. At each vertex, you will see three different colors that meet, red, blue, and green. And each edge now can be either empty or it can have one of two orientations. The orientations now are linked to the UQSL3 representations. And it can have one of three colors, which are the colors that I just introduced. So each link can now be in 7 different states. And the criterion to make this mapping work is that summing over the colors should give me back the undecorated model with the rules of Kuperberg. So here's a reminder of how that happened for the loop model. So I orient the loops. I give some local weight when loops turn left or right by giving some q to the plus or minus 1/6 because I turn 1/6 of a full turn. And if I sum over that, I get back my loop model. So the idea for the web model is the following. If I just had a closed loop, I needed to give it the weight 3q deformed. 3q deformed written out is q squared plus 1 plus q to the minus 2. So what I want to do is to associate the term q squared to red loops, 1 to blue loops, and q to the minus 2 to green loops. So that means that if red, blue, and green just goes through a 2-valent vertex, it's going to pick up either nothing for the blue, q to the plus minus 1/3 for the red, and q to the plus minus 1/3, but in reverse for the green. And this leaves the question, what happens now when the three colors meet? What weight should be given, and can this make everything work? So it turns out that the correct weights are the following. So up to the local weight, which are easy. I need to give a weight q to the plus minus 1/6, depending on whether red, blue, and green follow each other cyclically or anti-cyclically, and depending also on whether I have 3 ingoing or 3 outgoing vertices. So how to figure out this q to the plus minus 1/6? Where does that come from? Well, the first thing that you can actually see is that it will work. So for example, take this rule for a phase of degree 2. Imagine that the line that bubbles out is red. So that means that the 2 intermediate lines are blue and green, and I have to sum over those colors. So I have 2 terms on the left-hand side. If I now take the factors coming from the local terms, and if I take these q to the plus minus 1/6, it turns out that this will actually sum up to the number 2, q deformed. So I have my second rule, and also the third rule with a little bit more of a pain. It can be shown to work regardless of what are the colors of these 4 external legs here. They are taken to have the same color. Well, I think I am going to be very brief here. So the final goal will be to define a transfer matrix for this model. Okay, so I can transfer through my lattice in a certain way using small local operators. And I need my transfer matrix to be an intertwiner of the quantum group action. So I'm going to take a basis for the first fundamental, V1, V2, V3. I'm going to take another basis for the dual, so that they are indeed dual. I'm going to relate now V1 to 3 and W1 to 3 and the number 1 to the basis of up and down going red, blue, and green arrows, or an empty arrow. And then I need for my transfer matrix, the smallest constituent part of the transfer matrix that transfers me through one vertex. I need to draw the diagrams for all transitions. So here is one example. And what I'm going to be interested in here is just one of the terms, the tricky terms where 3 occupied edges meet. So let's look at this. So each diagram in algebraic terms can be written in terms of some elementary blocks, which are called VW, and evaluation and co-evaluation, and some tilde version of them. And their expressions, they actually follow from considerations on the quantum group. So the term that I need is a composition of the co-evaluation and W, as you can see here. It's a so-called zigzag identity. And if I write out this stuff that can be recovered by studying quantum groups in the basis of two spaces of edges going to one space in coherence with this diagram that takes 2 edges into 1 edges, when I look at it in the time direction, I'm going to get this matrix. And you see that it has 6 non-zero entries, which are q to the power plus and minus 6. And that looks familiar, of course, because those are precisely the q to the 1 plus minus 1 over 6 that I showed you before. So this is basically where it comes from. So that was a small technical part. So now we have a transfer matrix in this space. We can diagonalize it numerically. We can pick out the finite size effects, notably on the second line here, we can pick out the central charge of the model. And if I do this for a not so large system size, because the local Hilbert space is rather big, and if I take a particular value of q, e to the I pi over 5, for example, just to have something, then in the space of the 2 local parameters, x and y, I'm going to get this contour plot of the central charge. So there's going to be a huge region here, light blue, where the central charge is 4/5. And then there's going to be a special line, some ridge, along which the central charge is 6/5. So that is the equivalent of the dilute and the dense phase in the usual loop model. So this web model has, again, these dilute and dense phases, and that's true for any value of q. I can zoom in on the interesting region. You can see, indeed, I get the central charge 1.2. And using Coulomb gas predictions based on using these arrows to transform the model into a Hyde model that lives on the weight lattice of SL3. I can make Coulomb gas predictions for the coupling constant and for the central charge. And I'm going to get some expressions here that depend on whether I'm in a dense or in a dilute phase. And if I took gamma equals to pi over 5, as in the preceding figure, I will indeed get 6/5 or 4/5. In the 3-state Potts model case, there will be one point with 4/5. That's the dilute model. That's the usual critical model. There's going to be a dense model also with central charge 0. It's some generalization of percolation, but percolation now using 3 colors. So it's like the infinite temperature limit of the three-state Potts model is going to be critical, of course, not in terms of the Potts spins, but in terms of the webs. And now I will soon hit my time frame. I believe I have just 2 minutes. The loop model is integrable, as shown in particular by Baxter in an elegant series of 2 papers. For the webs, we can do something rather technical. So for the A2 case with a 7-dimensional representation that consists of fundamental and dual and trivial representations, we can indeed find some, using some construction that goes back to Jimbo, we can relate it to some known integral model, and once everything is done and said, then we are going to get on a square lattice and a model described in terms of diagrams with certain weights that is precisely equivalent to this model, and that is integrable. And there is no need to hide that the time is too short to show you these details. Let me summarize. So web models generalize the usual loop model to UQ-SLN, with a special emphasis here on SL3. It has a geometrical content with applications to ZN spin interfaces, in particular to the three-state Potts model. It has a dense and a dilute critical point when this Q lives on the unit circle. One can make a Coulomb gas description and compute critical exponents. And one can get integrable statistical models, not only for this model, but actually for all rank 2 spiders studied by Kuperberg. And one could imagine various directions. So for example, the usual loop model has been very popular in probability theory, where it has been studied by SLE techniques. But here the curves are branching. So the question is, can SLE do something similar? So with that, I hope I'm precisely on time, and thank you for your attention.
Yeah, thank you. Thank you, Jesper. Yeah, I did get the Yang Baxter photo actually in 2010. So,
yeah, you were the one who actually got it.
that was me. Yes. Sorry. So, are there any questions on your talk? Anyone can jump in online if they have a question. Just unmute yourself. Any questions from the audience here? Oh, Remy.
So I've seen other web kind of diagrammatic calculus pictures where they're also like considering like a fine SLN and a fine GLN categories. Do these other generalizations have any like lattice picture? These other web pictures? I'm not sure if you've seen them.
So for the moment, we have been mainly interested in either continuing with SLN. So with SLN, what you need to do was very briefly flashed here. So you are going to assign to each oriented edge some integer that lives in NZN. And then you will conserve these numbers at vertices modulo n. So that's one thing that you can immediately do using this very same model. The other thing you can do is you can take the other algebras of rank 2, so B2 and G2. So in those cases, it turns out that you will need either to sacrifice the orientation of your lines so that you just have lines without orientation. So you lose this bipartite property. Or you have two single lines that meet and turn into a double line. So you are going to have two kinds of lines. And that matches very nicely with a four-state spin model. So those cases we have investigated in detail. And I know that there are yet other spiders around, and so some part of this clearly has to also be done by other people. So feel free.
Okay, then Jesper, so on that note, we'll say thanks again.